It's a pleasure to introduce Peter Ward. Usually when we do these introductions, you go on about all the person's contributions to a field. And in Peter's case, you can really talk about someone who really helped create and grow a field of astrobiology. And he's someone who I've learned from long before I met him. When I got interested in this area, one of the first things I read was his book, Rare Earths, which I recommend highly and learned a lot from. And I know will be part of the ideas you hear in this lecture are ideas that were initially developed in that book. I also want to mention that this is the second lecture of the series, and the series will continue tomorrow at 8 o'clock here with the third and final lecture of the series. So let me give you Peter.
Thank you. Thank you. Thank you for coming on this cold night. I went out and bought a coat. It really helps. Tonight, I'd like to continue from last night. But last night was heavy lifting. We did a lot of science and a lot of intelligent design bashing. And I got home last night, and luckily, I was taken home by several of the Astrobiology Club, and we were able to drink a lot of beer and talk, which was good. But I woke up this morning feeling horribly depressed about intelligent design again. And I spent the day changing my talk. So this is all the intelligent design we're going to get, that cartoon. And I'd much rather talk about something more fun to me, which is astrobiology. It is a new field. It is really a new kind of science. And to begin, I'd like to start and think about what my friend and colleague Don Brownlee calls the astrobiology fever chart. The fever goes up and the fever goes down. And then through this talk, I want to expand from astrobiology to really some of the most interesting questions facing humankind. And perhaps one of these, obviously, is, are we alone? And are we alone as intelligent beings? Are we alone as life? Because at this moment, we still cannot say that humans and Earth life is not the only kind of life in the universe. We cannot say that there are other types of life out there. This might be the unique habitat for life in the cosmos. But for the rest of the talk, I'd like to try to tell you why I don't think that's the case. And at the end of this talk, after we talk about the aging of planet Earth, itself a somewhat depressing topic, at least it's in such terms of so many years away, that nobody in this room needs to worry too much about it, but our species may, is let's finally decide if we have to leave, where could we go? So we'll start talking about astrobiology, and we'll end out in space in Star Trek land, and somewhere in between, perhaps the two of these shall join. Well, from the fever chart, really, astrobiology could have many origins, but Don Brownlee, who put this together, really thinks that 1907, the canals on Mars, was one of the really seminal moments. And we had Percival Lowell, himself a fantastically interesting fellow, sitting at this not homemade, but certainly bought telescope, which is one of the finest of its kind, and seeing amazing things on the planet Mars. And this certainly influenced science fiction and novels for the rest of the century because he recognized this intricate pattern of what he thought were canals. The canals on Mars in 1907 were a great boon to those who would like there to be other life out in space, and why not? We can jump to 1953, when we have really one of the great first astrobiology experiments, the Miller-Urey experiment. And it was my great honor and pleasure to meet Dr. Miller 2 years ago at a conference, still spry, still talking about this very famous experiment where material was put within a beaker, it was boiled, some very basic chemicals, and out of this came amino acids, which are the building blocks of life. And from this experiment, for the first time, there was the sense that indeed, very simple material that could be found in space, given certain condensation, given certain heating, could produce the stuff of life. This was enormously influential and remains so today, because it is in the spirit of this experiment, this type of experiment, that a great deal of astrobiological research continues. Abiotic production of amino acids from a reducing atmosphere, the type of atmosphere thought to be on Earth, gave us scientific hope that life indeed could form from unlife material. We jump to 1960 in Project Ozma, and it's here now we find Frank Drake still hale and hearty and happy, the great honcho of SETI, the radio telescope from the movie Contact, and Drake indeed was one of those, a great pioneer who in 1974, this is his way of saying hello, trying to pump out material out into space and tell those aliens who must be out there that we're here, but at the same time, are you there? And from that, of course, came what has been called one of the two great iconic equations of the 20th century, the other being E equals mc squared. And this is the Drake equation, in which Drake, at the time, was trying to figure out how many intelligent civilizations might there be out there. Well, how would you get that? So here was this estimate. And the equation asks how many stars are there in the Milky Way, how many of these have planets, how many have suitable planets, how many of those suitable planets get life, how much of that life ever develops into intelligence, does it develop technology, and how long does it last? And it is a product of these sums that allowed him, if he could come up with some of these estimates, some idea of how many intelligent species might be out there. So the Drake equation was taken over by one of the great scientific expositors of the 20th century, perhaps the greatest of all, Sagan, shown here in this painting of him. Which observatory is that in? Lowell Observatory? There's this fantastic, there he is, Carl. I never had the chance to meet him. He died in Seattle, unfortunately. And he was a tremendous propounder of science as we know. His series Cosmos did a great deal in taking this idea, the astrobiological ideas, but he was a scientist as well. And this book, a translation of the Russian, was extremely influential in the 60s. From Drake's equation, Sagan was the first to really come up with what he thought were some pretty good estimates. At the time, no extrasolar planets had been found. We were just then getting some idea of how many stars in the Milky Way, but nevertheless, Sagan ran some numbers, and he came up with the estimate in this book that there should be 1 million alien intelligences in the Milky Way, which means that on this clear night, if you go out and look into the sky, you're probably going to see at least one star with an alien peering back at you. And so this became the high point, 1 million aliens in the Milky Way at the present time, the first estimate. We then have the Apollo program, and believe it or not, there was even thought that perhaps the moon might still have life in the 50s and the 60s, and yet when we get to the moon, fabulous place, lifeless. No water, no carbon, certainly not a habitable place in the least. And yet soon after, or at the same time, other discoveries were made that gave us hope for life in space. The Murchison meteorite, it fell in Australia in 1969. Those tearing this meteorite apart began looking at the compositions, were astounded to find 50 different amino acids. Again, the same building blocks that every protein is made of. The same material that the great Miller-Urey experiment was itself producing. Here's proof that the building blocks of life are in space naturally, and they even can be found within meteorites. So this is a tremendous boon, again, to those who hoped that there would be life in space. And then comes 1976. And virtually everything up to that date had been this great yes, 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 yes. And then we hit two Vikings with two big no, no. The Viking projects were extraordinary and expensive, $1.5 billion. Put two of the landers down successfully in a short space of time in 1976. They had life detection experiments. And the tests on Mars failed to find any evidence of life. But for one test, which is still controversial, Gil Levin's test, and indeed at the American Astronomical Meeting just a couple days ago in Seattle, an investigator from Washington State suggests that they did find life on Mars, and that it's life very different from our type of life. So there's been one very controversial experiment, but the reality of the Viking situation was that the community, the scientific community, drew back from astrobiology. This was a big, wet blanket. Now, Sagan had a really interesting part to play in the development of the lander. He was one of the chief scientists, and in his biography by K.A. Smith, It said that they took one of the landers out to Sand Dunes National Monument, and they put it on the ground, and Sagan went out and he rented a snake and a turtle and a lizard. And he walked out with a snake and his turtle and his lizard, and he put them down, and they ran back to the little shack, and they turned on the TV camera, and the camera could track the snake and the turtle and the lizard, and Carl said, "We're ready to go." Now, what they didn't let him put on were feeding troughs. Carl said we should put feeding troughs on because the Martian life would come out at night and be afraid of the lander in the day, but if we put bait troughs out there, they could come up. And so the New York Times said, "What type of life do you expect to find on Mars?" And he said, "I would not be surprised to find polar bears on Mars." And there's a famous New York Times headline in 1976, "Sagan expects polar bears on Mars." Now, what they wouldn't let him put on were headlights. He wanted a big light so he could see the nighttime nocturnal polar bears on Mars coming to the feeding tray. Now, how much of this Sagan really believed versus how much he was just trying to get all of us enthused. I mean, it's much more fun to have the experiment to look for polar bears on Mars than Gil Levin's little probe trying to find bacteria. I mean, how exciting are bacteria unless you're a bacteriologist or you're dying of some bacterial disease? So this was, everybody got upset and unhappy, and Carl made $1 zillion in books, and it was like a win-win for everybody except the science program, which after Viking turned from astrobiology, turned for searching for life, and began sending up probes that had no life detection experiments whatsoever. The planetary scientists kind of began to held sway in NASA, and we began to move away from this search for life. There wasn't a follow-up search for life on Mars till really Beagle, that failed British experiment of only a couple years ago. None of the rovers now have any life detection whatsoever. So Viking was a big cold water splash to everybody but Carl. Well, in 1977, other things were happening. The deep sea vents were discovered, and this was, at the time, certainly of no conceivable interest to NASA. But not for long, because one of the experimenters on the submarine in the deep Galapagos, the Alvin, who first recognized these unbelievable environments, far from life, that is made up of life using surface energy. Instead, we find life that is absolutely composed of brand new species, of a metabolism totally foreign to anything ever seen before. Life that deals with chemical energy from the vents themselves, rather than plankton or sunlight or anything from the surface. So here's a deep chemical metabolism and a great deal of life. But the other aspect of this is that life was living at temperatures thought to be impossible. Because of the high pressure, you can have temperatures of water far in excess of the temperature it boils out of the surface. 100 degrees centigrade here in air. Down there, under great pressure, you can have temperatures of 300, 400, 500 degrees centigrade. And life was found to exist at temperatures higher than that of boiling water. Bacteria. These extremophiles not only were found to be extremely interesting, they were found to be, from an evolutionary point of view, extremely ancient. And in the first Alvin ride back up, there's a famous quote. John Corliss said, "Gosh, I wonder if life could have started down here." And very quickly, microbiologists began going down. This got all the press, but it was the microbiology that got people excited about, could this be an area where life could have formed? And it is these discoveries, too, that got people really starting to think about life in space. Not Mars, but as we began to see more and more beautiful images from space, the moons of Jupiter, and eventually the moons of Saturn. In 1978, Voyager sent us back these images of this moon. Here we began to see that we are not the only planet, the only body that has oceans, because this is clearly ice, and it's cracked and it's broken. Another ocean was found, coming only a year after the discovery of the vents. Here, too, is a system where there could be no sunlight. But if you could have life at the bottom of an ocean, cut off from sunlight on Earth, why not life at the bottom of a planet, a moon in this particular case? They would have had hydrothermal vents too, because these cracks are being caused by flexing. And it turns out that this moon is so close to Jupiter that simply being close to it is causing a tidal flexing on the interior that produces heat sufficiently to melt the waters down below. It's liquid underneath this ice cap. And if there's enough flexing, there's going to be energy coming through. You can have a hydrothermal vent system. It's the same kind of life. And so from that deep sea dive, we began to think of life in space in these other oceans, and astrobiology came back into people's fore again. And now we know we have lots of these. Io, the closest, the poor planet which is flexed the worst, and then Europa. And as we get further out, Ganymede and Callisto, there's less energy. But it's Europa that seems to show the energy levels that would be sufficient, perhaps, for there to be life. And there's been a tremendous amount of interest. You have one of the great scientists in America, Chris Scheibe here, who has done more to understand the possible life in Europa, as well as many other things. It's my great privilege to see him tomorrow. 1980, another out of left field from last night, the KT impact, also had a huge effect on the formation of the new science that began to be called exobiology and morphed into astrobiology, because it was this that caused many disciplines of people to come together and start thinking about cosmic events. But it also started the philosophy of scientists from really disparate fields talking together by necessity. And in this case, it was geologists and astronomers. I was at some of these early meetings. I mean, it was like meeting a different species. A geologist talks to an astronomer and said, I know you exist, but I didn't know I could talk to you, and we couldn't talk to them. And a common language, there was some training back and forth. And some really interesting science came out of this. The KT discovery, this idea that an impact could cause mass extinction, that space itself could affect life on Earth so profoundly, really changed people's minds and began people thinking along new lines. In 1995, in the Columbia River, trying to clean up Hanford, this is my state, where there's probably more loose plutonium than there is in all the warheads in planet Earth, was percolating away, heading towards the Columbia River in those 1945 containments that have all rotted away. Scientists, not looking for bacteria, actually started getting bacteria from deep down, what is now known as the deep microbial biosphere. And within several kilometers of the surface, we now think there's a huge biosphere of microbes, and that these are existing on hydrogen, very primitive systems. Subterranean microbes of a significant biosphere living in places that could be Mars. And once again, this idea that perhaps we could bring in another group, and the microbiologists from the vents and the microbiologists from the deep subsurface began to join this army of strange, disparate scientists into this slowly growing together field we now call astrobiology. 1995, 2 extrasolar planets. This was a huge revelation. I was able to talk to Jeff Marcy. Really interesting. He said within 3 days of the publication of the first extrasolar planet, he was contacted by the Vatican because they wanted to know about the possibility, if there's extrasolar planets, converts. I mean, never too early to start thinking about a few more Catholics. Well, I mean, they had some astronomical interest too, but right off the bat, you got the Catholic Church on him. 1996, then, one of the great watershed events, ALH, and Don, of course, has painted the famous microbe green. Clearly, it is a blue-green algae like we have on Earth. However, my friend Joe Kirchvik at Cal Tech looked at this, and he said, wait a minute, those are the same structure I find in magnetic bacteria. These are magnetosomes. They are the internal part of a magnetic bacteria, which are among the most primitive on the planet. It makes perfect sense. And that debate raged for years. But it made its way all the way to Clinton. And the administrator of NASA at the time used the great excitement and the huge press, Life on Mars, to reorient NASA funds towards astrobiology. And from this came the NASA Astrobiology Institute, the first virtual institute, 10 early teams selected from many areas around the country came together as an institute to study astrobiology. By 2004, of course, we had the famous Mars rovers. still active so amazingly. Mars was wet a long time ago. In 2005, I think the mission that most struck me, this fantastic descent by the Huygens spacecraft led off from Cassini, falling down. And if that isn't the Gulf Coast in Louisiana, I don't know what it is. It just seemed that they must have, just like that terrible movie where we never went to the moon, yet we landed in the desert. But it just looked so Earth-like as that thing head on down and then splashed in this muck, which is very un-Earth-like. It's a wonderfully strange Earth-like world. Seed magazine contacted me about a month ago. I've written an editorial suggesting that we skip a manned mission to Mars and do a manned mission to Titan. So Seed loves this. NASA hasn't responded. And finally, 2006, Enceladus. This is the last of the really strange places we've seen. Yet another ocean. Tiger stripes on this strange moon around Saturn. And a lot of activity, too. There's hydrothermal activity taking place. We're seeing geysers coming out of this. We see a solar system packed with environments where there could potentially be life. And it is our species, I think, great calling over the next millennium, I guess, to explore each of these worlds. And I hope that we take up that calling, and that in the next 1,000 years, it will probably take that long, get to each of these bodies with an expedition and test for other kinds of life. I personally do not want to live in a universe where we are it. And my suspicion is that we may very well find some very strange beasties when we get out to these places. Hotspot on Enceladus, there are heated areas. And finally, in 2006, Don Brownlee, my friend and colleague, the successful principal investigator of the Stardust spacecraft. Here it is, a picture of it just rolled to a stop in the desert. And from it, we have found bits and pieces of the most ancient part of our universe. We have yet sampled samples from the most distant part of the solar system that have yet been recovered by humankind, and they're just showing all kinds of fabulous new discoveries. The spacecraft is still up there, and I was asking Don what we should do with it, because it's still up there. And we have decided, probably scientifically, the most valuable thing we could do is knock down the space station. Don and I talked quite a bit, and we were sitting at a table in about 1999, and we were both ragging on and on. Although we do believe that there's life in space, both of us got sick and tired of alien television shows. And it was about a 2-minute conversation that brought about this book, Rare Earth. And in this, we made a couple of predictions. We followed it up with another book that was better, but disappeared for the strange vagaries of publishing, called The Life and Death of Planet Earth. And I'd like to talk a little bit about what we think and know about the hypotheses proposed in these two books, one now 7 years old, one about 3 years old. Here's a picture now of Don's conception of planets, bad, good, and worst. And what I love about this is that as bad as Mars is, it certainly isn't as bad as Venus. But the other thing is, it really shows, I think, the difficulty if we ever do encounter any intelligent signal from outer space, because this is a PC talking to a Mac. It used to say bad, right? In PC it's bad, and Mac is bad. So, I mean, the difficulty now of just getting those two systems to talk to one another makes me a little cynical about the vegans. But he's correct in the sense that this is really a bad way for a planet to go. As planetary twins, there were obviously very different fates to this planet and this planet. Now, why is it that Venus is this horrendously hellish place with 800-degree centigrade temperatures on the surface, a carbon dioxide atmosphere? It's so bad, it's so hot, that the surface of it, every 100 million years to 500 million years, just totally bubbles up and melts. It doesn't do nice plate tectonics like us. It doesn't sit and just spout off a few volcanoes like Mars. It melts itself. This is a nasty, awful place. This place is nasty and awful for a different reason. Cold, small, probably lifeless, maybe not in the past. We hope there's stuff there. We hope that there's the stuff there now that we put there. Now, wasn't that going to be a pain if we come back and we find perfectly formed Earth life on Mars? That's the worst thing that can happen if we do find life. It means A, there's only one way to make life, or B, it's Earth life that got there, or C, it was Mars life to begin with and got to us, or D, it's our garbage that's up there. We really want to find aliens or nothing, but if we find Earth life, then we got another problem. So the rare Earth hypothesis was simple. It's just, we think that life isn't that hard to form. The Earth experienced the fact that the Earth got life almost as soon as it could have in a microbial sense. If you have water, you're probably going to have a good chance to have life. So we thought microbial life almost everywhere and complex life almost nowhere for a number of reasons to try to support that. It was a straw man. It was never named unique life. We got a lot of grief from two groups. And soon after the book came out, it was picked up by the New York Times. But there was a ABC anchor who had no date on Valentine's Day. I want to tell you the vagaries of publishing. And my publisher is in the front. He's going to close his ears and not listen to this. You like to think it was a greatly written work, but oh no. There was a headline in the New York Times that says, maybe we really are alone. And this woman has just been dumped by her boyfriend, and she said, damn right I'm alone. And so she got on the plane with a crew and flew up and interviewed us, and we were on national news, right? And the book shot up to #1. See, if that's a chance, I don't know what is. But then it was not argued that it was unique. And so soon after that, I was asked to go to a convention. Come talk about your book. And so I did. I took my 16-year-old son. It was at a huge hotel near Seattle. How naive was I? It was a science fiction convention. And we got out of the car. The first thing I see, not only is it science fiction and fantasy. But it's science fiction and fantasy and bondage, because here's this woman in leather and this guy being dragged by a chain. It's my 16-year-old virginal son going, Dad, what kind of place are you taking me to? An interesting one. And I went in and I sat down in a room, and there were this many people in it, and there were 4 famous science fiction writers. There was Greg Bear and 3 others I won't mention because I hate them. And for 2 hours, they just banged on me because I couldn't figure out why they were so mad at me. Well, I was taking their livelihood out of their hands and the mouths of their kids. Some little girl came up and said, my dad said you're the devil. I took their aliens away from them. But that was nothing compared to the reaction by SETI. And I had a number of debates with Seth Shostak. But my famous moment really was I was invited with a number of other scientists to Paul Allen's secret hideaway 30,000 square foot house. Now, it's hard to have a secret 30,000 square foot house in the Sandwich Islands. They flew me in the seaplane in the night. I mean, they didn't put bandages over me, but it was like that. And we get in, glittering hall, this beautiful place. And who do I see but Jill Tarter? And I had a copy of Rare Earth in my hand. And Jill was talking to Paul, and I walked up, and I wanted to introduce myself to Jill and give the book to Paul. And I walked up, and Jill's talking, and I hand him the book. And she looked at it, and you've seen it. It burns! It burns! Oh, she hated the sight of that thing because she was just hitting Paul up for $12 million for the Allen telescope array on that night. And here was 300 pages of reasons that she shouldn't have got the money. Well, she got the money. But boy, she's never spoken to me since. So why do we think there might be life out there? Well, the Earth history, origin of planet 4.6, origin of life 3.5. But, we can't find rocks in many places older than 3.5. We don't have undisturbed rocks. There may be more pristine Earth rocks on the moon than there are on the Earth. And that's another reason to go back to the moon, fossils on the moon. This is a nice paper from 2 UW astrobiologists who said, yeah, why not? Impacts blow stuff up into space. There's pieces of dinosaurs on the moon. That KT impactor put tons of rocks on the moon. That's a whole bunch of stuff going up into space. You're going to have some little T-Rex, but they're little tiny pieces. But we could find some really old Earth rocks there, too. So we'd like to know when life did start on this planet. It'd be very interesting to know how soon it got going. Because the earlier it got going, the better is the possibility that life is indeed early to start. But what is life? What kind of life? And here again, Rare Earth tried to break out 2 kinds, microbial life, single-celled life, from what we call metazoans. complex life, but then you have intelligent life. And when you go back to the definitions of intelligent life, it has to be you make a radio telescope. And that is the definition of intelligence to the SETI people. And I said, how about an English professor in a sonnet? Is that intelligent life? No, that's not intelligence. Their damn sonnet, we're going to throw it from star to star? That's intelligence. Radio telescopes. So unless you make radio telescopes, you're not intelligent. David, are you a radio telescope guy? Sorry, buddy. All right, the factors that we said, star size. It's got to be pretty big, and I'll tell you why in a minute, but not too big. Nearly circular orbits. You can have a high eccentricity in your ellipse. They're all ellipses, of course, but eccentricity is how far out it goes. Good Jupiter, no bad Jupiters. Oceans, but not water world. We don't know if this is true, but I think it's true. You would never make a radio telescope on a water world. Let's say you're a really, truly intelligent fish, and you get this idea, electrons. Now, if only I could find some copper down here. Fire! Damn! So you swim up to the top, right? Grow some fins and climb out. But on water world, there's nowhere to go. And worse, on water world, there's going to be no temperature control. And fun aside, I think you have to have a pretty narrow distribution of water to land, because if you don't have land, you're not going to have that which keeps our temperature essentially constant, which is the carbonate-silicate feedback system. We'll get back to that in a minute. And just how much water versus how much land there is an area of really interesting new research. And I think it's an area we really need to look at. Plate tectonics is that thermostat. And Danon and I suggested that to be a habitable planet for complex life, you would need plate tectonics. And I think that was the first time this is ever mentioned, but some Russian probably did it. Large moon, we said. I'm sort of backing off from that one. What does the moon do? The moon keeps our obliquity constant. Now, if we didn't have our moon, we would be flopping around. Mars flops around. Now, how fast those flops are is variable. But over million-year intervals, you could have your tropics become your Arctic, and your Arctic your tropics. That's not good for ecology. It's not good for plants. It's not good. Stability produces diversity. So how important is not flopping around? Our moon is quite a unique thing in this solar system for the relative size to the planet. And we thought about the stuff I work on, not too many mass extinctions, but maybe not zero. Maybe you need some critical number. And you've got to be in the complex life habitable zone. I hate this habitable zone. We're going to get to it in a minute. But if we're correct that you can, any place you have water, a little energy, all those moons of Jupiter are out of the classical habitable zone, which is the space where, in space, where liquid water sits on the surface. I mean, let's face it, you could put some bacteria in a jar and throw them out into space. They're not in the habitable zone anymore, and they're perfectly alive in the jar. So we need to constrain this whole habitable zone concept. So that's what we said. And it's apologies to Goldilocks, because it got more and more like that. This is just right, and this is just right. Plate tectonics is really crucial, I think, and I still think it is. This is what happens in plate tectonics. We have areas called subduction zones. And they're carrying rock material from down here, carbonates. And as it goes down, it melts. And when it melts, it comes back up, and it comes out as carbon dioxide. Now that carbon dioxide goes in the atmosphere and it warms the planet. And as it warms the planet and warms the planet and warms the planet, it causes weathering to increase. Weathering is the chemical or physical breakdown of rocks. And if silicate rocks start weathering and breaking down, that carbon dioxide chemically attaches to some of these and forms carbonates. And these carbonates start pulling CO2 out of the atmosphere, and it gets colder and colder and colder and colder. Finally, it gets cold enough the weathering slows down, but that CO2 is still going up in the atmosphere and it warms up. So you've got this constant feedback, up, down, up, down, up, down. It has kept our temperature never going below freezing and never going above boiling for the last 4.5 billion years. We do not think, with a star our size, that we can have a constant temperature unless you have this particular system. No one has thought up a feedback system. But look, you've got to have mountains. You've got to have rocks out in the air to erode, but you also have to have water to have subduction, because it takes almost a lubrication. It's more chemically complex than that for the friction to be allowed for these rocks to go down. Subduction takes place in water, but it builds mountains that erode to cause this feedback system. So now we're talking about not just an ocean world or a land world, you got to have both. So now we're getting really sort of specific in keeping a habitable world for a long time. Magnetic field, better have one of these too. So you've got to have a liquid core in there. And you've got to have a lot of radioactive elements in that core to keep your heat going. No heat, no plate tectonics. Mars is really cold and dead. The volcanic heat flow out of Mars is 100th that of Earth. It's a very small, dead world without a lot of radioactive stuff. This magnetic field caused by that liquid core keeps all the bad sun stuff from giving us really good Ray-Ban tans forever. The moon, again, I'm not sure if it is as important as we thought at the time. But this is Jupiter. One of the great papers was written in 1995. George Wetherill of Carnegie did a calculation. He said if Jupiter were not there, the Earth would be hit at a rate 10,000 times more than it is by asteroids and comets. 10,000 times. That's a KT catastrophe every million years or so, it turns out. That's not good for life. It's happened once in the last 500 million years. We had a dinosaur killer. If it's happening every million years or even 10 million years, then life really goes through a series. It's like if I give my publisher a cold right now, I hope I didn't. I had dinner with him. I think I'm okay. He's okay. But what if I gave him that same cold every 3 days, every 4 days, over and over and over and over? Sam would be dead pretty soon. And that's what these impacts do. Boom, 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 boom. And finally just a hell of it and die. And these are the worst. The asteroids are bad, but the comets are the worst. And the very worst are probably comets. If you could snatch a comet from some other solar system, that's the very, very worst because of the high speed. It's not just mass, but it's velocity, of course. The asteroids come and hit us at 25 kilometers a second, but the comets can hit us at 75 kilometers a second, so littler comets make bigger bangs for the buck. This is not good. And so this becomes really important, I think, in understanding habitable planets, the impact rate. So what is a habitable planet? Now we think of it as some place where temperature is all about water, 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 water. But this is really Earth life-centric, and tomorrow night I'm going to wear my white, totally white suit from South Beach and talk about aliens, because we are pretty Earth life-centric. But we'll talk about habitable zones and water at the moment. And water on a surface is a function of temperature. And this graph that came out in about this time, soon after rare earth, people started thinking about this. So here's the size of the stars now. These are itty-bitty stars, and these are great big giant stars. And the relationship down here is distance from that star. Now, our moon is tidally locked with us, which means it always has the same face to us. My father, when I was a young boy, said, "Prove to me the moon has a backside." I'm a biologist, Dad. That's physics. Forget it. It is, though. It keeps your same side. So let's say that we're a small star, and you've got to have water, so you've got to have this temperature that puts you inside this very nasty line, the tidal lock radius. And here goes one of the great fights between ourselves and SETI. And maybe it's a fight that still goes, because SETI is convening conferences on that. Can a tidally locked planet ever keep habitability? Let's say you're Earth, but your same face is always to the sun. And as you go around and around and around with your same face, you don't get the spin, you always get face. One side's got all the sun and one side never has any sun. Could you keep a life alive on that planet? And how complex could that life be? And that's where the fight is. And some people are saying the Terminator, just where you have that contact between light and dark, could be a thin zone of life. But this is, again, an indication of sort of the great frontier of astrobiology. These questions were unheard of 10 years ago. But the reason it's important is there are more of these stars in our galaxy than any other kind. If you say there are no M-class stars with the ability to have complex life, SETI is asking for a lot of money for no return, because you've just cut off a huge percentage. David, how many? What percent are M-class? A third? A half?
By number, more than half.
More than half. I mean, kiss them goodbye, SETI. So you've got to figure out that there's some physics playing with this stuff. So tidally locked, if it is fatal to life, it really reduces the possibility. It makes rare earth more possible. So the habitable zone of the system, I mean, here's the habitable zone Fat Tire Beer, a great microbrewery in Seattle. What better way to illustrate the beauty of liquid, right? And here we are in the beer zone. It's no longer the Habitable zone. It's the Fat Tire zone. And we sit in that beautiful beer zone, and we can make all the microbrews. Why don't we quit now? Go drink. All right, I've got to keep going. Late veneer. Where do we get our water? Turns out that the building blocks of Earth, from new studies, were dry. We're inside what's called the snow line. Everything should be built dry here, and there's lots of water out here. The Earth should not have had an ocean. So how do we get it? Once you're past the snow line in the outer asteroid belt, that's where you get your water. Lots of water out here, no water in here. And so what you need to do is bring it from here to here. You have planetary construction, big construction zone stuff. And what makes that possible is Jupiter. So you've got to have a Jupiter that early in your solar system history takes oceans of water and transforms it from outer solar system stuff and moves it to the inner solar system. But if you get too much of it, you become a water world, and you never get this complex life because you turn into this place with no temperature regulation, and you probably end up like Venus. So here we get this Goldilocks stuff just right. Nobody likes Goldilocks. That's not science. You know, it smacks of design. I said it again. So there's some paradoxes here. The looking building blocks are dry, and yet you've got to have the wet. So to build a system, then, we've got to understand how habitable systems form. And this is where the great revolution has taken place since rare Earth, because people on computers have been generating lots and lots and lots of models to show how systems do form. Turns out you need to think about not only space but time with habitable zones. This is star size again, and here's time. So here, the formation of a solar system with what turns out to be, in this particular case, an itty-bitty star, and here's a medium-sized star, and here's a great big star. Time is going on, and you can see this habitable zone, it's a distance now. This habitable zone begins to narrow, and this one narrows, and this one narrows. And why is that? It is because these systems lose the processes that keep them warm, and those processes are greenhouse gases. And it's the loss of carbon dioxide that eventually dooms any planet. The habitability disappears when you lose your greenhouse gases. How ironic. Here we are saying, reduce greenhouse gases, except it will kill us in the end. Reduce it just enough. Because this is a small star, it very slowly changes through time. Very large stars go through their main sequence burning. They burn their hydrogen into helium, and eventually they start enlarging in size. And unless you can move your planets away, if you've got a really big star, you're not going to have a long-lived system. In this one, the estimate here is that habitability ends 5 billion years. We're 4.6 or so. Whereas in some of the very small M classes, habitability here is shown at 6, but it could be much more than that. Estimates that some of these could have 20 billion year habitability. So small stars are very stable, big stars unstable. So you want something in between. So we could categorize habitable planets. We want them in a continuous habitable zone early, but since that habitable zone changes through time, it migrates because the sun gets bigger. You got to choose early, or am I going to choose late? It's like a campfire, except it's the reverse. We build this big campfire, and you sit at it, and what happens over time? It burns down, you move in, move in, move in. Except if it's a star, you're sitting here, and it gets bigger and bigger and bigger through time. Wait a minute, so you got to move out, move out, move out. Exactly the opposite of the old campfire business. Trouble is, we don't consider habitability really much in terms of space. We do it mostly in terms we do space and not in terms of time. And I think time is probably a really important, valuable variable to do this with. So we've got short-lived habitability or long-lived habitability, and we're going to find both in space. And the reason they are important is because we're just now beginning to start looking for candidate stars to try to find Earth-like planets on. So an overview then, let's take a look at terrestrial planet formation. It starts with a condensation from grains. There are then tiny little pieces called planetesimals They then grab together, and there's finally a late-stage accretion. And because of this four-step process, we can model these. And I'm going to show you one of these simulations. And this comes from Tom Quinn at the University of Washington and his graduate student. And you start out in your computer model, and it's beautiful to watch these things happen. Everything starts out at time 0, and then there are each particle, and there will be 1 million particles in this little simulation, are spinning around and told to grab other particles through time. And they do this. And what happens here in the simulations, you got lots of little particles, and they start getting bigger, and we start forming planets. And we finally end up down here with some planets. This is the eccentricity of their orbit. This is the distance from the star. And depending on initial conditions, you can have big planets, you can have little planets. And what's really interesting from these simulations is that you get all varieties of planets forming. Our solar system, we thought, gee, we're going to find the same solar system over and over. It's not true at all. And the discovery of extrasolar planets has shown that. We're finding a whole zoo out there. Giant Jupiters close in, Jupiters far out. Earth-like planets close in from the simulation. Sometimes Earth-like planets and Jupiters in there. But what we do know is when you get Jupiters close in, or Jupiters that are anywhere up this axis, the eccentricity axis, is all hell breaks loose, because the Jupiters are then bad Jupiters. And if they're eccentric, they take your Earth-like planets to go, choo, and either toss them out or toss them into the sun. So you've got to find a planetary system with a good Jupiter. So the conclusions from these guys, though, is much more hopeful that we're going to find beer than otherwise. The simulations suggest that there's a variety of Earth-like systems that can form. There's a large range of terrestrial planets in mass and water content. There's all kinds of stuff forming. I mean, it is a great diversity of life, not life, maybe life, but worlds out there. What needs to be done are develop better codes, of course, increase the number of particles by a factor of 10. Already we're using Beowulf clusters. I mean, this is huge computing to get these things done. But the lesson is that giant planets are really important. We ignore these at our peril. And when we began using methods for looking at Earth-like systems like the Terrestrial Planet Finder, we should be thinking along these lines. So let's think of a few other systems, multiple stars now. And again, in the rare earth, we began thinking, what about multiple systems? There's lots of these out here. Most stars, in fact, are doubles or triples. Would they be more or less likely to have habitable planets around multiple star systems? Well, multiple star systems are just as bad as the worst star. And in some cases, you can have very close together multiples, and perhaps your planets orbit the entire thing, or you have separate planetary systems around 2 or 3 stars separated apart. But what you worry about, once again, is gravity from one star grabbing somebody else's and tossing it. But what I'm trying to get done with Quinn now is asking the question, what is going to be the impact hazard in a multiple star system? Each of these guys, assuming that planetary systems are developing independently in a rough sense, are going to have their own field of comets, like our Oort cloud. Except they're so close, the gravity from one is going to be affecting somebody else's Oort cloud. And if the most dangerous thing is a comet from outer your system, even if it's a binary, then the impact rate in the binary systems may be too much for life. And that's a simulation we're trying to run right this minute. Now, we don't know what the answer to that is. But if it turns out that there's a less of a chance for developing habitable planets in binary systems, then SETI has to cross off another 50% of all stars. So we begin running out of real estate really fast. So let's finally think about the galaxy, and this is something that Don and myself and a man named Guillermo Gonzalez began to think about. And this goes back to the fact that probably the centers of galaxies are pretty nasty places. In the core, you got a lot of high energy radiation. And the other thing is, in the core, you got a lot of stars a lot closer to you than we do out here. Well, we're really lonesome out here. I mean, the nearest star, I think it's such a misnomer to say things are in light years. You know, Sirius is, 4 light years away? It's only 4. 4 isn't a very big number until you realize what a light year is. But if you're in the center of the galaxy, you've got a whole lot more stars, a lot more packed together. And once again, gravity from one star is affecting the other. And the impact rate would have to be higher. But impact would be the least of your problems. Gamma ray bursts, directed jets of gamma rays, could be taking out entire regions within the interior part of the galaxy. highly energetic bursts coming out of magnetars, black holes, and lots of supernovas. Dangerous in here. But also, for a different reason, probably not a great place to be on the outside. And the reason being is you've got to have heavy elements. Now, the astronomers here, for some reason, have come up with the most bogus definition that I've ever heard of. We'll hear it now. David, what is a metal?
A metal is anything created in a star.
Heavier than?
Helium.
Oh, a metal is anything heavier than helium. Now, that is not nonsense. Come on now. Oxygen is a metal. All right, well, that's what they say. So you've got to have this heavy stuff, the metals, the helium pluses, because if you don't have those, you can't get Earth-like planets. So where do you get those metals? You get it from supernova. Black holes and AGN cores, supernova, are the stuff that makes the heavy metals. When the Big Bang just happened, we didn't have enough time to have supernova yet. There could not be life in the galaxy or the universe for perhaps 2 billion years. Because it would be nothing, no metals, for what, 2 billion years?
But we get type 2 supernova fast.
All right, but let's just say maybe the first billion years there can't be life because there's no metals. You need metals to make life. It took a while to cook the supernova to build the heavy stuff. And the really heavy stuff, the stuff we need, like uranium, we need radioactive. It takes a long time to make. So we can really look at the galaxy. Here's the center of the galaxy, and here we are in radius and kiloparsecs away from it, and ask the question, what is the range of supernova formation as a function of distance from the center? And as you head out here, it's small. I mean, stuff thins out. The edges of galaxies are metal poor. There's a correlation between metallicity of a star and the presence or absence of planets. The edges of galaxies are probably too metal poor to allow the formation of Earth-like planets. The centers of galaxies are too energetic. It suggests that there's probably going to be some spot. This is our twin. We're in a barred galaxy. NGC 1433 is as good a model for what we look like. We're not Andromeda as anything. And if we were to draw a little line, we'd put it right here. So we published this in Icarus and Scientific American to a lot of catcalls. But it was a good idea. All right, what does habitability end to a planet? Let's move on from making a great place to how's it going to end? Well, suns enlarge. We've talked about this. Surface temperatures change, and the planet will have more and more and more heating. Global warming caused by the sun itself. When this happens, because of the energetics of more heating, you begin losing planetary circulation systems, and then you have two things happen. You can either have old age or you can have accident. But in either way, you lose life on your planet. Fate of the Earth, let's think about it now. Let's apply some principles and try to make some predictions now about how long we have for our planet. And the estimate now is that we have between 500 million years to 1 billion years before the loss of atmospheric CO2 kills plants. Once you kill the plants, you can run a calculation. David Catling of UW did this for us. It was about 21 million years to get down to 1% oxygen. No photosynthesis, no oxygen. Once you lose your oxygen, all your animals are gone. All animals are oxygen dependent. There are no anoxic animals on planet Earth. Global surface temperatures will continue to rise. When they hit 60 to 80 degrees, we lose our oceans. They don't boil away, but they're heading up into space. Actually, the Apollo astronauts saw the oceans going up to space right now. They rise up there in the disassociation. We lose the hydrogen to space, and the oxygen comes back down. But we will lose our oceans. And the reason this is happening is the continents keep getting bigger and bigger. Plate tectonics is making more and more continents, and we keep having shallow oceans getting deposited and lots of limestones. You go to the Rockies and you see those beautiful high mountains. They're huge mountains of limestone that is nothing but rock-hard carbon dioxide. Our CO2 has been locked up into the rock record. We can't get it back. But we could with a planetary engineering. Very simple. Get a lot of energy, solar energy, start blasting those rocks and making carbon dioxide. Or build cars forever. Could do it. Turns out CO2 has been going down. Now, here's 4.5 billion years ago, and these are large-scale estimates. In the present day, we're heading more down, 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 down. And because of this is what's causing our habitable zone to shrink at the end of the life of a habitable planetary system. Our Earth, based on this, is right near the end relative to its age of its habitable lifetime. Uh-oh. That's not good. Uh-oh. Come back. You died. I don't want to end my show. I want to come back to my show. I did. All right, let's look at the last 500 million years. This is the Phanerozoic. Here's our CO2 curve. It's been going up, it's been going down, but it's staying down through here. So this is where we are now relative to the time of animals. So it's as high as our CO2. This translates, this is about 6,000, 7,000 ppm, 10,000 ppm, and we're down here now at about 380. So we can model now, we can make some models in understanding how all this works, and this is a box model made by a group in Potsdam, and these are systems where you have positive and negative feedback. More solar luminosity causes greater temperature, more carbon dioxide, greater temperature, but there's also negative feedbacks. And so by working through these types of box models, this group in Potsdam has made the first attempt at estimating the lifespan of our biosphere. And they're using this sort of idea that temperature itself, this is productivity, and productivity is a measure of how much animal life, plant life, any life you have on a planet. So this is high productivity, and high productivity is a function of warm temperatures, but not too warm and not too cold, and your carbon dioxide. And the more CO2 you have at equable temperatures from 20 to 40 degrees, the more productivity you have. And so by using these functions now, we can put this into an equation and come up with an estimate. And here's the reaction or the results of these equations. We're seeing a couple of different starting senses, but in every case now, this is global productivity. This is a measure of how much carbon is being fixed into living tissue per unit time. The health of the life of a planet. High productivity means it's really filled with a lot of life. Interesting, the maximum is occurring before the start of animals. At 1 billion years ago, we didn't have an animal on this planet. We may have had a planetary-wide bacterial planet. We may have had more productivity with microbes than we do with animals. And the fascinating thing to me here from last night, we saw that diversity has increased through time. If we did a diversity curve from here to the present, it's up, 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 up. At the same time, if these models are correct, that productivity is going down, 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 down. There are more and more and more kinds of animals with less and less and less kinds of food, which is counterintuitive ecologically. If that's true, that's a very profound astrobiological discovery about the way worlds work. And you can follow these lines down, and here's the estimate. You hit 0 from here to here. Too advanced age is going to be a liability for a habitable planet. If you lose your CO2, you're just not going to get the other stuff. So microbes and metazoans, this is one of the reasons that we think that there's going to be far fewer metazoans, animals, than microbes, obviously. And we can start thinking about this now and look at what the loss of carbon dioxide does. It is a consequence of plate tectonics. See, this is the bummer about it. You need plate tectonics to have constant temperature, but the darn plate tectonics robs you of your carbon dioxide, which you need for life. Damned if you do and damned if you don't. Cause a change in the types of plants. We've already seen this. We have something called a C4 plant. We didn't have these 30 million years ago. Carbon dioxide is dropping so fast that evolution has produced a more efficient system to one more circle in the photosynthetic pathway. C4 plants are very familiar to us, the grasslands, most grasses, many shrubs, some trees. As a consequence of our planet dying under our feet. Loss of all plants at 10, catastrophe. And then comes heat. Here's the heat limits of animals and plants. Fish, 38 degrees, mammals, 42 to 45. All under 50 degrees centigrade. Bacteria, 113, and this has been raised way up since this slide was made, 150 perhaps. So the microbes can live at temperatures that we can't, and it's no surprise then that when we lose CO2, and then when we lose the oceans, we end up being a microbial planet. So let's think of the two fates of the oceans. One's a moist greenhouse, and the second is a runaway greenhouse. We're not sure which is going to happen here. Starts in a billion years, ocean lost to space. It's a lifesaver, well, bacterial life. Runaway greenhouse, if this happens, starts in 3.5 billion years, melts the surface of the Earth and kills everything. So this is two ways that after we animals die out, the fate of the planet resides on which way the oceans go. And now we can summarize this. This is the long-term age of the Earth, starting at the formation and ending up with the end of it. It's going to be about 12 billion years after the start. Temperature. And here we are now. And this is what I call the animal Oreo sandwich. We animals are the Oreo filling in between the two great microbial ages. The Precambrian microbial age and the after-animal microbial age. And this is probably what happens all animals, or all planets with complex life. And if we want to put on the fossil record of things, first animals are here, we're here, loss of the oceans begin here, and you begin to see what a narrow little window complex life is in the life of our planetary system. So we're looking at a time longer than all the time we've had yet, where there can't possibly be animals on this planet. So what happens at the end? Let's look at the final end of the Earth. And here we have to start thinking about red giants. This is Betelgeuse. It's going to go. This is the size of the star. This is the size of the Earth's orbit in relation to the size of that red giant star. That's big trouble. If you are a little planet in here, you are now carbon. So let's look at a model what's going to happen to our sun. This is now 12 billion years after the formation. So that's 7 billion years from now. And this is the brightness of our sun. Goes up about 10, and then it does some great big jumps. So the last 250 million years gets really interesting. There's a series of ups and downs and ups and downs. On the first up, we melt the moon. The Earth and moon begin to glow. And Europa becomes very nice real estate. Maui. Don and I love Maui, so we've decided that Europa will be Maui. And then the real end of the world happens out through here. And this is what we have left. Postcard from planet Earth. Because after that red giant collapses down on itself into a dwarf, and that becomes us. So that's the life and death of a planet. That will be our fate. Now, could it be that we humans could still be around by then? Well, if there's any life after we go through animals, it's going to be this, the Columbia River basalt stuff again. So the other fate, of course, is that we die early. We don't hit old age. We get hit hard. We get hit by a gamma ray jet. We get hit by a supernova. So I'm almost done. I want to finish up now and say, first of all, we've got to start looking out there. And the way to look for habitable planets is going to be through space telescopes of various types of space instruments and terrestrial planet finder and Darwin. We want to know these questions. And here's what TPF might look like, because we want to find others of these out here. So I want to finish up now. Let's just say that we humans got to get off this island Earth. This is one of my favorite old movies. And I love This Island Earth. How's this for intelligent design? 2.5 years in the making. I mean, that beats the Bible, but a factor of what? 1,000 or 3,000 or something. So yeah, this is they got out. That's Rex Reason, and they went off and headed off and found the metalloids and the mutants, and they came back and on and on. Great movie. All right. Why did we ever leave in the past? What were the present colonizations, pertinent colonizations? Well, these were they. I mean, we humans went all over everywhere, here and there and again, and the various voyages took place. Are any of these human migrations analogous to what is facing us as a species that we have to get out of here? So what caused those in the past? Well, they could be political. You got pushed out. You migrated to escape war, invasion, military. Vietnam caused a big migration out of the United States. Persecution. Australia. You got transported. Or social migration. Spread a religion. Reunite with family, friends. On and on and on. Marxism. Whatever. All right, this is the one that's probably going to happen to us. Resource or environmental push. There's no more food. There's no clean water. It's gotten poisonous. It's gotten hot. You can't breathe it anymore. You got to go. I mean, that's the fate of us on this planet. So let's look at some of the problems with going, and one of these is Biosphere 2, because if we go, where we could go are space colonies. And Biosphere 2 was this very expensive experiment in putting a dome over the Arizona desert and seeing if humans could sit in there. And I think some of you know the results of this. It was a complete disaster. It enclosed a gigantic space, 13,000 square meters of land in a total volume. And you think they would survive it. Here's what it was. They had big glass dealies, and they had a lung here, the human habitat, the rainforest, oceans, savannas, all this stuff. Anybody here ever go in it? It's open in Arizona. Somebody here must have gone in. There's somebody. And the results are 8 people sealed in the dome in 1991. Sustained these 8 scientists for even 2 years. They had to pull them out. Oxygen concentration in the air fell to 14%. That's like being above Mount Rainier. CO2 rose to 1,700 parts per million. That's worse than the Permian extinction. Nitrous oxide, 79 parts per million. This is 2 years in a system that was built, it's on Earth, to be completely self-supporting. And it's bigger than any space colony you could ever imagine out there in space. This is a big problem for orbiting colonies. They killed all their species, all this pollinated species died. I mean, this is terrible news if you want to send a big colony ship out into space, you know? It really went sideways, and this doesn't take into account the lawsuits. But NASA has a website on why we should go into space. And here's what I love. Growth. Key advantage to space settlements, the ability to build new land, blah, 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 blah. Great views, low-G recreation, environmental independence, automated gated community, and what I didn't put on, sex in space, zero-gravity sex, and they got all this stuff on this website. It's great. Take me. Furthermore, survival. Yeah, well, that's true. That one's true. But power and wealth. Let's see, survival or power and wealth? I'm going to leave. I want out of here. Let me go. But where are we going to go? We're going to go to Antarctica? We're going to build undersea colonies? Look, it's going to be a hell of a lot easier to colonize Antarctica than it is Mars. You can breathe in Antarctica. And yet you can't really grow a lot of stuff there very well. How about off the Earth, the solar system, Mars, asteroid belts, or orbital colonies, or other stars? I mean, this is pretty much what we have to do. To get there, we've got to use available technology or build new. I don't think available technology will get us out of the solar system. And we've got to take stuff with us. We've got to take vegetables. You've got to eat your vegetables. You've got decomposers, nitrifiers, animals or pets. You've got to take dogs, right? Can you see it? You know, the Earth is about to get burned up. Do we bring the dog, or do we leave the dog home? I mean, 5 humans or 10 dogs. And how about the cats? Oh, God. And the canaries. And then you got my kid loves gerbils, and on and on and on it goes. Are there any reasonable stars among the nearest 100? Well, people are looking now, and this is a deadly serious look. And this is, again, why we need TPF. Well, who's going to go out there? You know, you're going to build this big spaceship and head off to a place you don't even know if it has an Earth-like planet. And you can't even send a generation that'll land there. The case for Mars is as close and as feasible. No one owns it. There's a great case. First come, first served. I claim this in Princeton. We could call it Princetonia. And it puts our species on 2 planets, which is a good thing in a day of meteors. But the case against Mars is even stronger. You know what's going to happen? The odds are, I went to a human in space workshop. The odds are that if we send, I think it was humans to a year-long Mars experience, 30% of the men and 45% of the women will die of cancer prior to their time. Some will die of cancer really fast. The radiation hazard on Mars, the radiation load on Mars is huge. And unless you're totally shielded, you cannot live on Mars in colonies as we see. A glass dome will kill you. It's far worse than we've ever seen in any of those darn movies. Nobody gets cancer in the movies. The propulsion systems, there's just nothing around that can get us to the stars. I mean, it's just chemicals won't get you to ion thrusters. Nuclear engines can start thinking about it, but fusion or antimatter, I mean, we're talking absolute science fiction for the technology to get us out of the solar system. It's not to say there aren't wormholes and all the good stuff, but we can't foresee that at the moment. Why is it so difficult? Because of the distances. I mean, it takes a long time to get anywhere with the thrusts and the stuff that we have today. New types of engines will have to be developed. So the solutions, how do we send humans? Well, hibernation maybe. Better exercise out there, because all those humans coming back from space now are in pretty bad position. None of them are working in the Olympics after they go in space. Maybe we can genetically modify little itty-bitty humans. Conclusions. I think we're here to stay, at least for the next 1,000 years. We'll visit the planets but not live there. No way to colonize the stars. So my suspicion is we're stuck. But, you know, we do make beer. Thank you. You can either listen to questions or go hear the president.
Okay, so let's give people just a minute to walk out quietly, and then a few minutes for questions. We'll have to a few minutes for questions.
How much longer? We can sing the song, "It's the end of the world as I know it, and I feel fine." No questions? Come on, let's give me a question.
Question?
Please.
Sorry.
If you have a question, please use the microphone.
I have two questions. One is, how does what you present change the probabilities in the Drake equation? And the second question is, silicon is a very common element on Earth, and it may be in the stars. What about a silicon-based life form that's out there someplace?
What you doing tomorrow night? Silicon life is tomorrow night. I'm going to present you with actually a very plausible silica life form. They're called silanes. It's silica carbon. It's what we would find on Titan. If there's life on Titan, it's silica life. And in terms of the Drake equation, you know, think about the Drake equation. Any of those factors in the Drake equation that approaches zero, the whole thing approaches zero. So what we did, we called it the rare earth equation. We added in a bunch of stuff, like the need for plate tectonics and the need for the Jupiter and this and that and the other stuff. And it makes the numbers really dive. No, there's us, so we certainly do have one. My guess is there's 3. But last week it was 10. Another question, please.
You mentioned the sequestering of carbon dioxide and the fact that without the plate tectonics that you don't get the release of those rocks because there's going to be a formation of a giant continent. But we had a giant continent before. I mean, why is it not possible that giant continent would in turn break up and the cycle would continue? What is the evidence that this cycle will really end?
Yeah, we did have a giant continent before, and you saw the carbon dioxide curve did drop down and go back up again. And this was related to the formation of Pangaea and then its breakup. And once it broke up, we were actually liberated a whole lot of carbon dioxide, but we did it because we had a whole lot more volcanic activity. When the continents all come together, it slows down tectonics, and you really drop the amount of CO2 coming out of volcanoes. But when they break apart, there's these big flood basalts, and it pumps it way up really fast. So that's why there's a variability. But if you take that away from the 500 million year graph and look at the 4 billion year graph, that blip becomes so tiny, it's really a straight line down. And so we could have some squiggles in it, but that's why it's a 500 million year to 1 billion year estimate. That give back and forth is related exactly to the things you're talking about. We should expect to have another supercontinent. We can predict it in 250 million years. We will all be one supercontinent. We can tell this from plate tectonics today. And I predict there will be just a monster mass extinction then, if the past is any clue to the present. Please, sir.
On your curve of the CO2, looking at the back, many million years, it's much, much higher than now. And there were many kinds of life back then. Why, since the CO2 is so low now, why are we worrying about the global warming if the CO2 now is so low?
Yeah, it is an interesting conundrum, isn't it? We're certainly looking at CO2 values now that are much lower than they have been in the past, but on my curve last night, we're going to go right back to 70 million years ago in the next 100 years at the most. I mean, see, it's taken 70 million years for this to get to the level it is, and we're going to change that in less than 300 years. When you want to talk about how powerful we humans are, to me, that's the most powerful point. That it's 70 million, 300. That's what the industry has done. So it's an amazing changeover that's taking place.
Tremendous scope of what you said. It's a fabulous lecture.
I have a lot of great colleagues.
Your publisher was smiling a number of times during it, too. I noticed that. This seems like the best argument I've heard so far for the anthropic principle. I'm curious why you're depressed about intelligent design, and except that I have this theory, which you can tell me whether you agree with it or not, is that it's an alternative explanation other than the fact of this equation that everything's going towards zero as to why the Earth may be unique. And intelligent design, I don't know that it says the Earth is unique, but that might be something you could read into it. I might say, by the way, that my roommate in graduate school here, just retired from University of California, was John Baumgartner, was the pioneer in geophysical modeling of mantle convection and so forth. And he happens to be a creationist, very leading geologist. So not everybody's depressed about creation, but very interesting lecture. Thank you.
Thank you so much.
So, in the context of the increased carbon dioxide as a result of human activities, is there any realistic possibility that deliberate intelligent life could significantly extend the age of animals by manipulating carbon, by shielding the Earth and space from a brightening sun, etc.?
Yep.
And does that significantly change the calculations?
Yep. Totally. We can extend the lifespan of the biosphere through engineering 4 billion years, 5 billion years. I call this the Medea hypothesis again. You survive through engineering. As an environmentalist, I hate it. As a species, I love it. We got hands, baby. I hear the bar. Any other questions? Thank you for coming.
There are more questions.
Oh, there are. All right. Oh, excuse me. No, go ahead. Go ahead. You can be the last. Now, the last question last night excoriated me for being a big jerk, so you can have that honor.
My question is, do you think that reading your book had any impact on Paul Allen's decision to take control of the ATA project away from SETI and give it to Berkeley?
Can you repeat that? Reading my book will take...
Do you think that your book had any impact on Allen's decision to take control away from SETI and give it to Berkeley?
I've talked to Allen 4 or 5 times in my life, and each time I talked to him, he didn't know who I was. So I don't think so. Paul Allen's too busy to read my book. Oh, I have lots of books not published. My publisher knows. He's hoping his isn't one of them. Thank you.